I've been so busy doing stuff for my wife for Mother's Day that I haven't actually eaten anything yet today. And that's a problem because 18 months ago I was diagnosed with type 2 diabetes. The only thing that has gone down my gullet today was the metformin and the glipizide that's supposed to keep my blood sugar down. So I've got like the shakes and I've got the low blood sugar, right? Just to give you a sense of how much trouble I'm in. Here's the last time I got an A1C test. Yes, I'm showing you my medical record. See how much I care. So it's 8.2%. Now, those of you familiar with diabetes know that that's pretty bad. And you can even see where my doctor's like scolding me for like getting a bad test grade. And now I have to like get this drug, which is like $1,000 a month. And she wants me on this one. And this one I have to like inject in my ass. And I really don't want to do that. Right. So, all this is to say is that the only thing that's in the house for me to eat is a giant chocolate muffin from a set of giant chocolate muffins that I got for my wife for Mother's Day, right? And it's like, oh, it's a giant chocolate muffin. That'll solve my low blood sugar problem. And then I look at the nutrition facts and it says, um, 80 grams of carbohydrates in one chocolate muffin. Well, 80 grams is what I'm supposed to eat in an entire day. So I have not had anything to eat. This is the low blood sugar edition of World's Finest Physics, going over the AP Physics 2 practice exam. Hopefully, you've seen my other videos so that you know already all about my professional development session for physics teachers. It's mechanics. So, if you only teach physics 2, I'm not sure if that's going to be something you're interested in, but you can see kind of what we're going to focus on. You're more than happy to tell your math teachers at your campus about my math teacher session. We still have spaces available as of this recording. And the idea is to just increase student engagement with hands on activities and math based games. And if your math teachers are doing a better job, then that makes your job easier. And, just like I try to appreciate my wife on Mother's Day, let's appreciate our math teachers that are at our campus. Can we take some extra time to do that? I think Teacher Appreciation Week just ended. I don't even know what day of the week it is. That's how out of it I am. If you're a student or a parent, or if you're a teacher and you're interested in referring students to me, I'm certainly happy to help them out. Probably a little late now for this year, but you're more than welcome to send them to findphysics.com and I'd be happy to help anybody out. All right, this is the part where I make fun of the College Board and I make fun of Golden Corral. Golden Corral really isn't bad food. They just happen to have the same typeface letters. It's Roboto Slab, in case you're wondering. That's the name of the font. And I noticed that just like a month ago. I was like, hey, that's the same typeface that the College Board uses, right? So I'm going to make fun of Golden Corral, even though it's actually pretty good food, and it's kind of a treat when I take my family there. They're not bad people at all. They work really hard, and the College Board, they are actually bad people. It turns out they're just a bunch of principleless scumbags, as far as I'm concerned. I mean, look at the way they got called out by the governor of Florida, right? And it took them like an entire weekend to fold like a origami expert who's on speed, right, on methamphetamines, right? So there you go. College Board, your profile in courage. You make Fredo Corleone look like Atticus Finch. All right, so here we go with this. Do I even have like a decent printout? I think I'm running out of ink. That tells you that the ink in the printer is doing about as well as my blood sugar. So I haven't read these yet. That's probably going to be a huge mistake on my part, but here we go. I'm surprised you're even still watching after all this time. I have no energy for this. All right, this is like what? Let's see. There's six mechanics and six EMAG because there are two sets of each. And so five P1. So I've already done 17 problems. By then, this is going to be 21 of these. A rectangular tank with a mirrored bottom is filled with water. A beam of light passes from air into the water. Okay, index of refraction is greater than air. We should know that. You shouldn't have to tell us that. Sketch the entire path of the beam as the beam enters, travels through, and then exits the water. Oh, where's my straight edge? I don't know where my straight edge is. Here it is. Okay, so I guess I'll make the beam of light red. I feel like that. Okay, I sure hope my kids don't come in here and start screaming at me. All right, I have enough of a headache as it is. Okay, so I know that the light is going to refract closer to the normal because this is a higher index of refraction material. So the higher the index of refraction, the smaller the refracted angle, right? But then, this is going to be the tricky part, I have to make this reflect at like the same angle. And I really wish I had, like, I don't know, maybe a grid in the background so I could show that it's the same angle or something like that. That's supposed to be the same angle. I'm going to call that theta R or something. They have a name for it? No. Okay, and then when it comes back out and then exits the water, it's going to exit the water and it's going to have the same theta I like that. So the theta I becomes a lesser theta R. These all of these theta R's are all the same. Those are all the same because of law of reflection and because of alternate material angles. I don't know any of those freaking theorems from geometry. All right, well, whatever. Okay. Sugar's an out of the way. Ah, fuck you! Oh, with this sugar. Oh, gosh. I can't pause the video. I'm going to go get that cupcake. Okay. If I have that cupcake, I can't eat anything but zucchini for the rest of the day because zucchini has no carbs. Okay. Oh, I can't even stand the word of it. Resulting in a mixture that has different index of refraction than water. My blood has an index of refraction of water right now. The student considers two models, A and B, of how sugar. I'm in tears every time I see that word. I'm going to cry right in front of you here on YouTube. The models are shown in figure 2. Model A, uniformly mixed throughout the water, resulting in a mixture with index of refraction. And it was greater than okay. Mario is better than Wario. What's with the M? I guess M is mixture or model. I don't know who came up with these letters. Okay. And I say that in general, like who even came up with like the Roman letters, right? I'm saying that in the vaguest sense possible. Layers are formed of varying concentrations. Let me tell you about varying concentrations of sugar. Okay, there are three different. Like this is torture, man. This is like hate crime or something. The top layer is only water. The middle layer has the same concentration of sugar as the Model A. I can't even stand this. I have 4 of these I got to do. Okay, Model A. Describe how the observed wavelength of light changes as the beam travels from air into the mixture. Okay, so I'm going to tell you some things I know. I know that when you travel from medium, I'm going to write this medium 1 into medium 2. We all know n1 sine theta 1 equals n2 sine theta 2. But did you know that you can use the c equals, oh, no. It's v equals n over c. You can use this like c equals n times v to come up with n1 v1 is equal to n2 v2. Like that's the relationship between index refraction and the speed of light in a material. It just reminds me of Snell's laws, like n sine, NV, right? I envy somebody who has the sugar water in front of them. Okay, and then you can also say V equals lambda F, and the F is the same. It's the only thing that stays constant as you go from one thing into another. All right, so what if I said this? What if I said N lambda equals N lambda? So this is on the formula chart, but these are two things that might be worth it for your students to remember and you to remember too. Okay, so here's what I'm going to say. I'm going to say since the sugar water has a higher index fraction than the air, right? The speed is less, but the frequency is the same, right? So V equals lambda F, less speed, same frequency is a shorter wavelength. So the wavelength does shorten there. Okay. Uh Oh my gosh. This is more confusing than a menu at Golden Corral. I don't know. I'm just going to make fun of them. I mean, I have them right here, right? They have the same. I mean, look. Have you actually looked at this? Like, look at the little flag on the G, like right there. Like, that's the same thing, right? Look at the kind of the way there's a little elliptical circle there, and it makes kind of the corner like that. And then you can look at. It's not exactly the same. Oh, look at the L's with their little serifs they got there. It's really the same. Ooh, and look at the D with his little serif at the bottom and the top. It's the same. It's Roboto Slab. You can find it on the internet. Okay. Determine an expression for theta 4 in terms of theta I, NA, and NB. Okay. So I've got a funny story to tell you. You look at this and you're like, oh, well, this is going to like refract and then refract and then refract. And so this is going to be theta 4. Is that what theta 4 is? Yeah. So this is theta 4. And maybe we can call this like theta 3 and theta 3. Well, is that what it's called? Yeah. And then we can call this theta 2, right? Like, does that, and then this is also theta 2. So funny story. So N air sine theta initial equals n water sine theta 2. And then n water sine theta 2 equals n mem sine theta 3. So I'm just doing Snell's law there, and then I'm going to do Snell's law there as well. N mem sine theta 3 equals n b sine theta 4. So you see, all these Snell's laws are all equal to each other. N times this angle equals n times this angle. N times this angle equals n times this angle. N times this angle equals n times that angle. So they're really just all equal. So really you just say NA sine theta I equals NB sine theta 4. Just skip all the Neapolitan that's in between. Man, I could use a Neapolitan right now. Yum. Okay, so I'm going to divide NA over NB sine theta I, and then I'm going to inverse. Can I just tell you, folks, I can't stand this notation with the -1 symbol. Like, it looks like a multiplicative inverse to me. I'll call it arc sine. Okay, like that. The people in Europe have it. Like, you people drive on the wrong side of the road over there, but you at least know to call it arc sine rather than sine with a -1. It looks like the multiplicative inverse rather than function inverse. Rank the angles from greatest to least, with one being the greatest. What was the ends? Do we know that the ends are most, middle, least? I mean, I feel like that's the case. Yeah. M is better than water. And then NB. Did they say that NB was more than NM? Like, can I just assume that? Did you actually not say that? Did you not say explicitly that NB is better than? Is that, am I just to assume that? You didn't actually say that explicitly, College Board. And I didn't write this problem. This is not my fault. One of the future ones in here I actually wrote part of. It got heavily edited. I don't think I'm going to show you the draft for that because it got so heavily edited. But they never actually said. So am I just to assume that higher concentration? Okay, well, whatever. All right. So one being the greatest. So theta 1 is the greatest. Okay, wait a minute. So theta 1 is, oh, no, 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 no. Sorry. No, let me try this again. It's theta 2 is the greatest. Theta 2 is the greatest. Why? Because the ranking of the angles is the opposite of the ranking of the indices of refraction. Okay, because the indices refraction go up, the angle goes down. So help me out here. The N of air is the greatest. The N of water is the next. Then the N of the mixture, and then the NB. So the angle in the air is the greatest. Then theta 2. Then theta 1 and theta 3. Then theta 4. Right? Okay, because these correspond. These angles correspond to these ends. I'm not going to write out the word indices refraction. So, two, one being the greatest. Okay, figure this the frick out. This is why you don't use a fucking pen on a fucking AP exam. Okay, okay, that's the ranking. This whole 1, 2, 3 business is so confusing. With one being the greatest, seriously, make one the least. It's the least number. This is not poker, or the one is the highest card. Jeez. Oh, back to this. Will this problem ever end? Yes, it will. Okay. For the original tank filled with water, the beam is observed to exit the surface of the water a horizontal distance dw from the entry point. I'm assuming they're talking about this dw, right? From the entry point for models A and B, the horizontal distances are dA and dB respectively. So this would be less than that. That would be dA. They're both less. They're both less. I'm pretty sure they're going to be less. Okay, sorry. I thought I had to rank these compared to each other. Sorry for the dead air time there. I was looking at this. I'm like, I don't have the sugar for this. I don't even. I really shouldn't even be doing that. I don't even think I'm okay to drive. So, All right, so that's the DA and that's the DB. That's got to be less than DW. So both DA and DB are less than DW. This is justify your answer is because it's a determine. So just say the answer, but then justify. I have to justify it. Why is this? Because I can't even think right now. Okay, this is because in the sugar water, okay, in the sugar water, the angle, I'm going to say the beam of light is steeper, rising closer to vertical. So the beam does not travel as far horizontally. And you know what I might even do? I'm going to change colors, even though that's not really something you're allowed to do because these are scanned in black and white. Okay, where I'm gonna be like or something like that, like the dotted lines above. You have to the student has to reference the diagram in the writing in order to give the reader permission to look at the diagram. So dotted lines show the beam in sugarless water for comparison, sugarless water, which is what happens when you combine metformin, and glipizide, and no food because you've been so busy doing nice things for the mother of your almost be five children. She banged out on one ovary. Okay, students are given an unknown circuit component that is connected into the resistor of known resistance. Okay, so obviously it's a cylinder. What's so unknown about that? The students are asked to experimentally determine whether the component is a resistor or an uncharged capacitor. Boy, can I relate. Complete the following diagram to show the use of standard circuit equipment to determine whether the. Okay, what do you want me to say? I mean, here's what occurs to me. The battery, okay, switch, and then I give you like an ammeter here or something, a voltmeter, I suppose. I freaking don't know. All right, describe the experimental procedure to determine whether the component is resistor uncharged capacitor. All right, I'm going to say the ammeter and voltmeter can make measurements thousands of times per second and create I versus T and V versus T graphs. Okay, I'm gonna like this is a freaking like Lab Pro, Vernier. Those people, right? They keep pestering you to buy their overpriced crap. Okay, so here's what I want to say. I'm going to say close the switch and take I versus T and V versus T data after the switch is. Isn't that that's like one sentence procedure. Like, is that all I had to say? Just close the MFing switch. I mean, what results would the students expect the components of an uncharged capacitor? Okay. Support your answer in terms of potential difference in charge. Okay. So the I versus T graph would go from V over, let's make this a 9-volt battery. Okay, from 9 volts over 500 ohms to 0, and have this shape. Okay, I versus T, right? And the V versus T would go from 0 to 9 volts. and look like this. Okay, so here's a V versus time as the capacitor charges, right? And so this is because the capacitor takes time for charge. Okay, I talked about charge to build up on the plates. So, V equals Q over C. As the Q increases, the V increases to an asymptote. All right, I teach AP ASY. I teach AP Physics C, Electricity and Magnetism. So I'm quite familiar with this setup. Whether you're Physics 2 kids or not, are familiar with it or not, I don't know, because they don't really do the calculus for these shapes. When I taught Physics 2 back when my district supported it, I did teach them these shapes. I just didn't teach them where it came from calculus. Okay, now the students conduct a different experiment, the EMF of a battery that is not ideal and has internal resistance 30 ohms. The battery is connected to a variable resistor in a circuit. The students measure the current. Okay, again, I haven't seen this yet, but I do know that if I walk around the loop, an equation relating to, so I always wrote the loop rule this way. I always go around the loop and I say, okay, the battery's a gain, and then everything else to drop, like IR and I capital R variable or whatever, equals 0, kind of like that. So that's what I'm going to do there. Okay, so how am I going to play this? Okay, what if I factor out? What if I don't really like this. Okay, if I bring these over, if I factor out, I say E minus I, because I'm trying to linearize the data right now. Can you tell that's what I'm trying to do? R plus R variable equals 0. Okay, so you hopefully aren't colorblind like the scanner for the free responses. That's a variable. That's a variable. So in pink, I've underlined variables, and I've underlined constants in green. So what am I going to do? I think what I'm going to do is this. I am going to bring this over. So let's bring it over here. Okay. So EMF equals I, R plus R variable, like that. You see that there? Okay. And now I need the two variables, one to be on top of the fraction, the other one to be on the bottom. That's how I linearize. So if I do this, if I say R plus R variable on the top, and the reciprocal of I in the denominator, then what I can do is that, so this is the answer to this question. This is me just trying to, this is the slope, this is the rise, and this is the run. So the horizontal axis is going to be 1 over I in the reciprocal of amps, and the vertical axis is going to be R plus R variable, R plus R variable in ohms. Okay, so what I'm going to do here, R plus R variable is going to be a joke. I just have to do 230, 330, 480. I can do this in my head. Yay. Okay. But then I have to do the reciprocal of data here from AP Physics 1 exam. Okay. So, nope, I didn't mean that. I still didn't mean it. Okay, let me put this where I can see it, where you can see it. 87, 60, 42, 27, 16. All right, list 1 times 0.001. Okay, that makes it correct. 200, 300, 450, 700, and 1200. Okay, so I am going to do this. I'm going to do L2 plus 30. That's going to add 30 to each of those. And I'm going to do 1 over L1. Okay, and so what's that going to give me here? That's going to give me 11.5, basically. Screw you, significant figures, and screw you if you believe in them. 23.81, 37.04 basically, and 62.50, something like that. I don't know. Okay. Oh, now I have to plot it. Okay, I'm gonna have to plot it now. All right, 1, 2, 3, 4, 5, 6. Well, that was nice of you at least. Oh, wait a minute. Okay. So this is gonna be 1200, 1000, 800, 600, 400. This is so exciting watching me make a stupid graph. 1, 2, 3, 4, 5, 6. Okay, so that's going to be 12, 10. No, wrong. Let me try that again. This is going to be 60, 50. Don't take your AP exams in pen. 30, 20, 10. Okay, so here we go. This is 1 over I in amps to the negative 1. This is going to be R plus R variable in units of ohms. Okay, so let's see. I'm going to find me a 230. That would be 240. Each of these would be 40 here, and each of these would be 2. So a 230 would be about right here. Okay. Now a 16 and some change and a 320, 330 about right there maybe. Okay, and then a 23. Just this makes my head hurt. I just don't want to even do this. Okay, this is how much I care about you. And really honestly how much I care about you maybe signing up for my PD session so I can like have company over the summer and get to know people and maybe we can learn some great physics techniques together. I don't know if I did that correctly. That looks like 37, doesn't it? Because that's 38. Whatever. Okay, 62.5. Right. You can come and keep me company. And all right. So that's my dots. Are you going to force this to go through the origin? I don't know. I feel like it should. I feel like if you have zero resistance, that would be infinite current. So yeah, why not? All right. Using the graph determine the well, this E is the slope. E is the slope. So you can either do bleh and 1200 over 60. You're kidding me. 1200 over 60. Is that seriously like 20 volts? Which I got from 1200 minus 0 over 60 minus 0. Let's see what the calculator has to say. Lin reg, Quinty, does it say 19.5? Hey, that's really close. Oh my gosh, it's over with. All right. So this question is one that I sent them. It is pretty heavily edited from the initial draft I did. So I'm just going to show you really fast, like what the initial draft looked like, so you can believe me that I did actually create. Like you saw there when I was looking through this, when it was coming off of the printer, and I saw this, and I said that looks like something that I would do. Work or school account problem. You know what my problem is? Is that I'm using a school computer ever. Okay, so, yeah. So they made this problem substantially easier than the one that I sent them. So you should send them some love for it. Okay. Tank X is a cylindrical tank filled with water. The bottom of tank X is connected to a pipe. Valve is closed. Two blocks A and B, identical dimensions. Okay. Float and are partially submerged. The water and air can be modeled as consisting of individual particles that are continuous rate of motion. In terms of the inner with both water and air, explain why there's an upward buoyant force on each block. Okay, so the water molecules randomly collide with the sides and bottom of the what are we calling these? Block of the block. Okay. Of the block exerting forces normal to the block's surfaces, right? Okay. Air does the same on the sides and the top. Okay. And the top. So air does the same on the sides and the top. So here's what I'm going to say. I'm going to say all the side forces cancel, and water being more dense. Um, the water molecules produce well, I don't really want I want to yeah, I guess water molecules produce upward force on the bottom of each cube or each block or something like that. I was going to say that the upward force. Oh yeah, I am going to say that. Produce maybe more upward force on the bottom of each block than air pushes down. Sorry about this. I'm halfway through this and I'm about out of gas here. Okay. The valve is open. The water flows out to the pipe. The surface of the water moves downward. When block A touches the bottom of the block B is still above the bottom of the tank. So block A has greater density since a greater fraction of its volume is below the water line. And I'm going to just show this to you with an equation really quick. So when an object floats, its buoyancy force, which is the density of the fluid, volume under the water gravity, is equal to gravity, the gravity force mg. That's the buoyancy force and the gravity force. But the gravity force can be written this way. Watch carefully. M is the density of the object, the volume of the entire object g, and the g's cancel. So the more dense the object is, assuming it still floats, the more volume is under the water, you see. Okay, tank Y is a large tank with an open top to air. The bottom tank Y is connected to a short horizontal pipe radius R. The closed valve tank Y is filled with water height H naught above the horizontal. Y is specially designed so that when the valve is opened, the surface of the water moves downward at constant speed Vs. Derive the relationship between the speed Vp at which water exits the pipe and the height. Okay, so this is going to be a Bernoulli equation, right? So what does the Bernoulli equation say? It says pressure plus rho g height. Okay, I might be changing that in a moment. Plus 1/2 density V squared equals pressure plus rho g height plus 1/2 density V squared. Okay, now what do I want to say? I guess I'm going to say, uh, what are they? Is it P? What's the P? Okay, so so P. This is going to be point P, the pipe, and S is going to be the surface. So pressure at the surface, height of the surface, velocity at the surface. Pressure at the pipe, Y at the pipe, velocity at the pipe. Now, I'm going to tell you this. I don't know if this is still the case, but this is the case back in the AP Physics B days. When they had to do a derivation with Bernoulli's equation, they had to actually spell out all the simplifications they were going to do, like explicitly say that the pressure at the surface equals the pressure at the pipe since both are touching the air, right? So that gets rid of that. And then the Y of the pipe is 0 because we set that as the origin. Okay. Now there's not enough space here to do all that. So I don't know, but I'm going to do rho G Y. Okay. And then Y of the surface is H naught. Okay. Rho G H naught plus 1/2 rho VS squared equals 1/2 rho VP squared. So let's get rid of the rho's. Let's multiply through by 2. And then I think that's it. If I multiply through by 2, 2gh naught plus vs squared equals vp squared. So then you just take the square root and then we're done with that. Derive the relationship between vp and the changing radius r. Okay, to show of the top surface. Well, this is just AV equals AV. This is just continuity. This is just continuity, right? So continuity. So we're going to do the area at the surface, the speed at the surface, the area at the pipe, the velocity at the pipe. The area at the surface will be pi big R squared VS. The area at the pipe will be pi little r squared VP. Okay. So we said the horizontal pipe's radius is R. Did they ever say anything about the big R before now? They really didn't. Okay. So then we're going to cancel out the pi. And then we're just going to divide, and big R cubed over little r cubed VS equals VP, which is squared. No, not squared, which is what we said there, squared there. All right, when the radius R of the tank is sufficiently greater than R, the speed VP can be approximated to justify this claim. Okay, so I'm going to say this. I'm going to say if R is really big compared to little r, then VS is very slow, and VP equals radical 2g h naught plus VS squared becomes VP equals square root of 2 GH naught. Why? Where happened to the H? Okay. Oh, it's a height H. Okay. Well, then let's just call that height H then. Okay. And it just becomes an H. Why? Since VS is very small or slow, maybe. I don't know. Okay. Does that make any sense to you? I mean, it makes sense in my mind. Oh, somebody's playing a clarinet or something like that. And they're going to. This is how I empty the spit valve out of my trombone when I was in 6th grade. Okay. Tank Z is a large tank. It's open to the air. The bottom of tank Z is because does the speed Vs at which the surface water moved out increase? It decreases for sure. Okay, referencing equations from BI and BII. Okay, so let's look at BI. Okay, so here's what we're going to say. We're going to say that the VP at the pipe decreases as the height decreases according to VP equals the square root of 2GH plus VS squared. Then we're going to say the R increases in this pipe as the surface goes down, right? Okay, as the surface goes down, using r squared over little r squared, Vs equals Vp, the increasing, oh, well, let's just do this. Let's just say Vs, that's not squared, Vs equals Vp little r squared over big R squared. As R increases in the denominator and VP decreases in the numerator, VS decreases or slows down. All right, I'm going to tell you right now, this was a much better question than the one I sent them, so I'm happy that they used my setup, but that was a much more fair question. So good job, y'all, at the College Board. You get a rare compliment from me. Okay, now, number 4, I'm almost done. I'm being screamed at by my 2-year-old. Okay, particles A and B have positive charge. Okay, I can't even read anymore. Students Y and Z discuss the electric field and electric potential point P. After the third charged particle is going to be placed over here. Student Y, if the particle has positive charge plus 2q, the magnitude of the electric field will be 0. No, that's wrong. And to make the value of the electric potential 0, you need a negative q. That's also wrong, but it's partially correct. So what I'm going to do is I'm going to say this. All right, in a clear, coherent paragraph language, evaluate the accuracy of each student's statement. Okay, so student Y is correct that a positive charge must be placed at the empty corner to create up left electric field to cancel the down right electric field from the plus Q's, right? Except symmetry demands that plus 1Q be placed at the bottom corner. So all 3 plus 1Qs at corners of the equilateral triangle will create electric fields that cancel to 0. Now that was just student Y. Now let's talk about student Z. Z is correct that a negative charge is needed to cancel the positive potential of the positive charges, right? It would look something like this. It'd look like V equals K Q over R plus K Q over R plus K what over R to equal 0, but we need negative 2Q to create enough. I mean, it's 1Q and 1Q plus something equals 0, and all the K's are the same and all the R's are the same because it's an equilateral triangle, right? So to create enough negative potential to make potential at point P0 or something like that. I don't know. I don't think the blue part of that sentence really worked really well, but I was running out of space and I'm running out of brain. Okay, so particles A and B are once again held as two vertices equal a triangle. Students want to represent the electric potential energy of a system of particles when a third charged particle is brought from very far away, bottom right vertex. In scenario 1, the third particle is a positive Q moved from very far away to the bottom right vertex held in place. The bar is shown following to the electric potential energy of the system because all three particles when the third particle is very far away. In the grid provided, complete the bar chart. Draw a bar to represent the work required to move the third particle of positive charge very far away, the bottom right vertex. Draw another bar to represent the electric potential energy of the system and say, okay, well, I may be running out of brain, but I still have enough brain for this. So here's the initial potential energy. The initial potential energy is KQQ over R, where D is this distance right here. So we only have KQQ over D. That's the initial. But the final is KQQ over D, this pair, plus KQQ over D, this pair, plus another KQQ over D, this pair. So we're actually going to go from 1 to 3. We're going to go to 3 times as much energy. So this is going to be 3 times as much energy, which means that the work is going to be double. This plus this equals this. The energy you start with plus the work equals the energy you end with. Maybe make it look a little bit prettier. But yes, it is 3 times as much energy. Now we have a particle with negative charge. Okay, so the initial potential energy was KQQ over distance, both positive. The final energy is KQQ over distance. That's the two positives. But then we're going to get a negative KQQ over D because of positive negative, and another negative KQQ over D. So it's going to be plus a KQ negative Q over D and plus a KQ negative Q over D, which is going to make for negative 2 KQQ over D. So we go from positive 1 to negative 2. So we're going to end with a negative 2. Okay, so, I got to do the math on this one. 2 plus something equals negative 4. So that's going to be negative 6, isn't it? Okay, so negative 6. No, that's wrong. I'm sorry. Shame on me. This is what you get for not using fucking. Okay, no, this is actually just positive 1, negative 1. Okay, so this was supposed to actually be this. Okay, so don't have your students do this. Grade the purple response. Okay, that's a joke, son, because it's going to be scanned in black and white. Okay, sorry. All right, so that's negative 2. So this is going to be negative 4. I told you I'm running out of brain. Okay, it should actually be this. Okay, so you have the positive potential from positive times a positive, and then 2 negatives makes a single negative, and my favorite 3 words ever. Okay, all right. Well, you know what? If you suffered through all of these videos with me, even the calculus one, why? Honestly, I mean, that's like 5 hours of your life thrown away, right? But I do provide these as a service and also to advertise the support that I give to physics and math teachers and to individual students. So I hope you enjoyed my videos. I hope that this wasn't too boring since my brain is shutting down right now. You know what I'm going to do is I'm going to go fix myself something. My wife is content right now. She got all the treats she wanted for Mother's Day. And so I think I'm going to make myself myself, I'm just going to go eat that muffin. Okay, screw my doctor and screw 80 grams of carbs. I mean, I should anyway. All right. So I guess I'll see y'all next year unless I make some neat videos in the meantime. I'm hoping to make some new ones soon. So subscribe to my channel if you want to get a notification that new videos are popping up because I make them sometimes for students and sometimes for teachers, sometimes for both. All right. Yay, butterfly pattern. That's my wife's design choice. Catch you on the flip side.